I'm Jim Soland. I'm a second year in the program, and it's my pleasure to introduce Andrew Ho. As a lot of you are aware, Andrew was a student here working with Ed Hartle, and is now at Harvard by way of the University of Iowa. And just to mention a couple of things that might not just sort of be readily apparent looking only at his CV, I've had the opportunity to go to a couple of Andrew's training sessions at different conferences, and I've been really impressed in a lot of ways because in addition to sort of looking at some of the biggest issues that are going on in education and policy and measurement, he can sort of cut across all of those different areas. And not only that, but speak really intelligently and clearly to lots of different audiences. I've seen him talk to psychometricians and to sort of State Department of Education officials, and he makes the material really accessible to all of them. So a really unique confluence of skills. And I think you're going to see a bit of that in his presentation today. So without further ado, Andrew Ho.
How's the sound of that? Ooh, wow, okay. Pretty good, I guess. Yeah. Great. So thank you, Jen. That was a really, really nice introduction. And he was saying that he deserves like a frequent visitor card to my talks, and he'll get a discount on the next one or something. So I wanted to start by saying a couple things. I'm just taking the clicker and put it in my pocket. I want to start just by saying that if anyone has any questions throughout the talk, feel free to interrupt me. I'm happy to field any questions during the talk. And also, as Jim noted, I was a student here from 2000 to 2005, and then I came back for a visiting scholar position for 2009-2010. It's been great to be back and see so many familiar faces, and also to see what's sort of changed and stayed the same. And this is a very, very impressive room. I hope all of you down here in the comfy chairs don't fall asleep. So the title of my talk today is Between the Ordinal and the Interval, Educational Score Scales and the Scale Dependence of Analytic Results. And the point that I'm going to try to convey here is that whenever we see any results, the idea is that we want to have kind of glasses on, and we want to be able to distort the lenses a little bit, and that's what this is about. It's like the idea is like we're distorting score scales, and we want to see if our inferences change. So the image if that metaphor is all helpful. It's the idea is like whenever you see any kind of results that use any kind of analysis that uses educational test scores, try to imagine that you have glasses on and you're only seeing one part of the picture, and you want to sort of see if this distortion changes your impressions of the results. And I'm hoping to convince you that this is important, and also introduce a practical framework for accomplishing this. So I want to start actually though with a little bit of a story about psychometricians more generally. So when I was on this visiting scholar position a few years ago, I had lunch with Rick Hanishek, and it's great to meet him. And he said I just want to sort of share a little bit of the story. He said, I'm always wary about talking with psychometricians because they always tell me what I can't do. And so I just wanted to start by framing, the endeavor of psychometrics. And I'm going to try to be today a can-do psychometrician, right? Because I think a lot of us, and Ed's very much a can-do psychometrician, so I'm aspiring to that example. But I'm going to try today to be a can-do psychometrician and not be so cynical all the time. And so I think, just to give you a sense of why this is, so you appreciate it if you know psychometricians, I think we actually just reflecting on our field. We psychometricians, we raise our test scores, and not raise our test scores, but raise and nurture our test scores, and so we develop this, I think, kind of attachment to them, right? So it's like we care about them, and then I feel like we can be a little bit protective of them, such that if someone goes off and uses test scores in a way that we're not happy with, we get very, very defensive and protective of them. And so the idea is that they're kind of like these baby chicks that we all raise very carefully, and then we send them out into the wild, and we want them to be safe. And so that's where this is kind of coming from, I think, is in the field of psychometrics, we are often very, sometimes to a fault, protective of our test scores. And I'm going to try not to do that today. I'm going to try and give people tools so that they can be protective themselves. So part of our job, I think, as psychometricians must be to sort of anticipate the dangers of the wild, like setting our sort of baby test scores off and letting them go and get sucked up into these crazy accountability systems. We have to know what's going to happen. We have to anticipate what's going to happen and be very precise about the pitfalls. Right? So that's what I'm going to try to do today. I also want to reflect briefly on how policy metrics arise, because I'm interested in how scaling decisions, this sort of distorting our vision, ends up affecting the policy metrics that have consequences in today's educational sphere. I actually reflect on policy metrics often. I'm a psychometrician who's very interested in policy metrics. And so I want to present what I'd like to call my Mount Rushmore of recent educational policy weasel words. And I like the Mount Rushmore phrase because it's like these are the top 4 of the moment, right? And so these are weasel words that confound us and encourage us to use test scores in unusual ways. And so here's my Mount Rushmore. So there's Mount Rushmore. I would call this proficiency. That's one of my weasel words that I'm very fond of and have critiqued often. Here's adequate yearly progress. I'm not sure why this has to be Jefferson. But here's a career and college readiness, and then the 4th is growth. And so this is what I would think of as my Mount Rushmore of weasel words in educational policy. And what is a weasel word, right? A weasel word builds artificial consensus. We all think we're talking about the exact same thing, but in fact, when we dig deeper, we all realize that we're in fact talking about different things. And so they are dangerous because of that. They allow us to build consensus, but then, of course, in implementation, we all come up with different metrics. And so they often inspire what I like to call these Frankenstein metrics, right? So test scores are not the be-all, end-all anymore. Test scores get sucked up like our little baby chicks, get taken off into the wild, and they're subject to bizarre machinations, right? Bizarre aggregations and adjustments of scores with many judgmental decision rules layered over, right? And often combined with other metrics in bizarre and unpredictable ways. So I think we should kind of appreciate this process. The metrics that we have functioning in today's educational policy context are not the scores that psychometricians are typically familiar with, but really these kind of bizarre Frankenstein metrics. The other way to think about it is they also inspire kind of Rube Goldberg accountability. Right? You know Rube Goldberg machines, they're like these bizarre contraptions that end up doing very simple things. For example, school accountability worksheets that require 100-page long guides for schools to fill out, dozens of acronyms and annual revisions. So that's just to say that the metrics that are functioning today in policy are not the typical ones that lots of psychometricians are used to dealing with. They are these bizarre Frankenstein, Rube Goldberg kind of procedures, and we have to have appreciation for that as we set our chicks off into the wild. So many fundamental statistical and psychometric concerns are dwarfed by the consequences of hidden decisions in these processes. Right. So what we in psychometrics have spent a lot of our time thinking about and doing, and a lot of statisticians and economists are thinking about and doing, we create these metrics, and just like the baby chicks, we're like, look at this is great. And then it's like they get, again, sucked up into this bizarre policy process, and what ends up actually making a difference is far less what we've taken so much care to raise, but this bizarre sort of sequence of developing new policy metrics. And so I want to sort of keep this in mind, because that's sort of how I think about this whole process, right? How can we take psychometric perspectives and think about how they have an impact through this Rube Goldbergian process, right? So that's how I sort of see the world. Others interact with this process in consequential ways. So I don't want to say that statistical and psychometric concerns are not important, right? In fact, the whole argument of this talk today is that they are. But that appreciating statistical and psychometric concerns without attention to this process is missing the impact of our work. We have to appreciate when and in what circumstances these psychometric concerns have an impact, and in which circumstances they don't. So I think of this interaction between statistical and psychometric metrics and this sort of policy metric Rube Goldberg machine. The interaction between the two is what I'm interested in, and what I'll be talking a little bit about today. Okay. So that's sort of how I see the world. I'm interested in these interactions. And here's an outline of the talk. So I'm going to start by just giving you this is like the sort of direction. I'm going to say, how does scaling, the psychometric concerns that Ed and I and many other psychometricians deals with, how do they influence these accountability metrics downstream? How does scaling influence accountability metrics? So I'm going to talk about what's on the left-hand side first. I'm going to define what a scale score is. Then I'm going to talk about what I mean by an accountability metric. Then I'm going to talk about 3 different ways that scales can have an influence on accountability metrics. 3 different levels, and I'm going to sort of phrase them as a hierarchy. And I'm going to motivate focus on level 3, scale dependence. So talk about why I think that's a good lever for talking about this. Then I'm going to describe a general approach to quantifying level 3 scale dependence, and finally describe the magnitude of dependence and compare them, to compare the dependence across metrics. So the idea is, again, how much does distorting our lenses, right, make a difference as far as the consequences that we see? Okay, so I want to give you like just a little bit of a flavor of the kind of results early on, and then build the narrative to how I get to the results. So this is the form of my findings. It looks a little bit, so the idea is that, what is the metric? The metric that I'm going to choose to focus on for this particular finding are what we call growth percentiles. And growth percentiles are one of the more widely used growth metrics out there today. Some of you may be familiar with student growth percentiles, which are used in, I think, around 12 states and many other districts as well today. So I'm going to actually rank different ways of getting growth percentiles in terms of how scale dependent they are. Right, so the idea is, how much does distorting your glasses, right, change what you're seeing? And the answer is, it depends on the metric. Right, that's the whole point, right? So like how does changing our glasses actually change what we see? So this is the form of the findings, right? So here are different ways of getting growth percentiles. So these are all the different metrics that we might consider. Percentile ranks of residuals, student growth percentiles, and these percentile ranks of residuals have forced normalization, and these percentile ranks of residuals don't. And so I'm not going to define these metrics as much as demonstrate that, as much as try to make the point that each of these metrics kind of interacts with the scale dependence in different ways. So over here, we have sort of a general measure of scale dependence. And so these are actually invariant to scale. So this approach to getting a growth percentile does not depend on a scale transformation. This approach does a little bit, and this approach does a lot. So the way that we might interpret this is that a typical median student can expect her student growth percentile to be pliable, right, to change in response to this distorting of glasses. In a range of 3 percentile points on the percentile rank scale. Right, so that's how we interpret that 3. And so the idea is that some metrics are more distortable than others. Right? And here, for example, a typical median grade cohort can expect its mean student growth percentile to be pliable in a range of 0.086 standard deviation units. Right, so the idea is that, again, like depending on the metric that you use, you can anticipate that your glasses are going to lead to more distortion than others. Right, so the idea is we can actually rank different metrics based on how distortable they are. And if scale distortion is a concern, we might want to choose metrics that have less scale dependence than others. Because this is the form of the findings. How can we look at all the metrics and procedures that we use and rank them in terms of their scale dependence? This is again the outline, so I'm going to start by defining score scale and think about what this process is of changing the focus on our glasses. So first, what is a score scale, and how are we even allowed to change our focus, right? So scaling is a process of associating numbers or other ordered indicators with the performance of examinees on an educational test. This is Mike Cohen at the University of Iowa, and this is what I always show when I try to illustrate how we can interpret scales. This is actually the NAEP, National Assessment of Educational Progress Scale. And if you Google NAEP item maps, you'll see that they actually have a fairly thoughtful way of, again, associating performance with particular indicators. If you zoom in here, and you ask, what is proficiency really? Right? They actually have these item maps that allow you to sort of appreciate this, right? And the idea is that if you have an individual score at 307, you're likely able to accomplish this kind of task, right? So this tells you what students know and are able to do if they have particular scores in this range. So if you ask what proficient is, well, it's around, they're probably not as likely to be able to do these, but more likely to be able to do these kinds of tasks. Okay, so this is an educational score scale. What then is an accountability metric? How do scaling issues, the question I'm asking today is, how do scaling issues, we can think about as the ground level, how do they impact metrics that matter at higher levels of aggregation and adjustment? For example, the growth percentiles that I just showed, other kinds of value-added metrics, adequate yearly progress, and so on. Right? So the idea that I have here is that, what we're used to in psychometrics is thinking about individual student scores. But again, the metrics that we deal with in practice today are not individual student scores as much as aggregations of them, right? So the question is, how is it that is it or is it not the case that that these distortions at this level have impacts on these higher order levels of aggregation? Right, so some metrics will dampen this ground level instability, and others may be more distorted. Right, so actually, given that we're an earthquake country, right, this is maybe like not a bad metaphor, right? That there are these foundational concerns in psychometrics, and some buildings, that is metrics, if you will, have these dampeners. And they say, if you use this metric, no matter what goes on at the ground level, the people on the 24th floor, they might sway a little, but they're not really going to be affected. Right? Whereas other buildings, right, other metrics, are such that if there's a little bit of shaking at the ground level, they might come tumbling down. Right? And so this is what we want to look at the interactions between this ground level instability, if you will, and these higher order metrics. Right? And again, we've been concerned for a long time in psychometrics with this, and I think we need to be more concerned as accountability metrics rise in importance. This, and this. Right? That Rube Goldbergian process. So here then is a hierarchy of definitions of scale dependence. So what is this shaking at the ground level, right? Actually, it's not a bad metaphor, right? Because there are different ways of shaking, right? Aren't there like S waves and W waves or whatever it is?
You
right?
thought of this in advance.
No. So actually, Jim knows. Like, I sort of thought about this the first time I presented, but the more I think about it, maybe it's even better. But yeah, there are different like ways. So what are 3 different kinds of like shaking at the ground level, right? So level 1, I'm going to describe as the most fundamental, which is if we pull the carpet out, like mixing metaphors, if we really shake up the ground, right? We could think of changing the whole domain or dimension itself, right? So imagine if we think, okay, instead of a reading test like the National Assessment of Educational Progress, what if I pulled that out and slotted in, for example, the Stanford 9 or Stanford 10, right? So that's one way that we can talk about scale dependence. We can say, here's a metric calculated on one scale, that is one test. Then I can yank that out and say, what if I calculate that metric with another test? And this is something that's actually quite commonly done, is that as a number of you know, we can do these cross-test comparisons. And that is a way of asking, does the scale matter, right? So that's what I would call level 1, level 1, most foundational way of addressing scale dependence. And it's a solid way to go about things. Level 2, we can talk about scaling as equating designs or scaling decisions. So there's a way that, in psychometrics, we link test scores together, and that process in itself, which you may have seen if you've taken some of Ed's classes, these equating and linking metrics, right, or different modeling decisions can have an impact on our metrics as well. And that's another way that we can talk about scale dependence. At the 3rd level, and where I'm going to be spending most of my time today, is scale as equal interval assumptions. So that is after you select a domain, after you select an equating procedure or model, even after all of that, you have a sort of level 3 scale dependence that's asking, do you have equal intervals at each point in the scale? So now let me define briefly, because this was the title of the talk, between the ordinal and the interval, what an interval scale is. And Jim and Ben have seen me do this before, but the idea is like, you should be able to go like this with your hands, and have equal intervals, and put them at 2 points, different points in the scale, like one right here, and say one right here. And the idea is that you want to have some argument that you can make that those 2 intervals are in fact equal. And of course, the idea is that you're holding up equal intervals, and so of course they're equal. Like, what's the controversy? And the response to that is, no, really equal, right? Do you really have some substantive argument that the distance, for example, between 200 and 300 on the SAT score scale is meaningfully equivalent to the distance between 600 and 700? On what basis can you make that argument? Right? And that actually is a very tricky thing to do from a psychological, substantive, educational standpoint. Right? On what basis are we really claiming that these 2, if I measured them, they certainly look equal. In this physical example of the ruler, sure, one's 1 inch, and here's 1 inch. So yeah, they're equal. But in an educational, psychological context, there's rarely a foolproof argument that really allows us to say with certainty that those two intervals are truly equal.
Andrew, is that because, I just want to make sure I understand, I like what you're saying, but I just want to make sure I understand that the underlying phenomenon is not the same at different points in the measure.
Right, for equal intervals,
Right.
That's right. So like if you're talking about, for those of you who might have kids, you see these growth charts over time, right? And actually, you have to have kids to know that kids, like, they sprout up and then they sort of like plateau over time, right? And so the question is, right, does growth mean the same thing, right? At like a low level of the scale, does like 1 inch mean the same thing for a kid who's like 3 months versus a kid who's like 2 years old? And the interesting thing about that is in this physical example, that actually is true. They're both an inch, right? But the question is, do they like imply something fundamentally, like with regard to your intuition about what that distance means? And in education, right? Claude and I were talking earlier today about SAT score scales, right? And is the difference if you're Stanford University making selections, right? How do you treat the distance between 600 and 650 on the SAT scale versus like 750 and 800? Right? Both are 50.
Right.
But do they have the same implication as far as like the difference between student proficiencies on those two gaps?
And I imagine this is exactly where you're going, but it also depends on if you're looking at the measured object or the role that the measure is playing in some other regime. It seems to me it's largely the latter.
Exactly right. Yeah, and so that's actually why when I present this ordinal versus interval levels of measurement, it's a really tricky thing because it forces you to really grapple with what scales do, right? It takes you right to, like you were saying, the sort of downstream uses, right, and whether or not those distances have equal implications for those uses. So that's, I think, a very challenging argument to try to make, and it's why I think the framework that I'm showing today is important. Is because it does show how some metrics are more susceptible to being distorted by these assumptions than others. So I want to briefly talk about levels 1 and 2 because when you think about scale dependence, I don't want you to forget them, but then I'm going to forget them and talk about level 3. So levels would be, and this is also to say that it's not like this idea is new, right? People have been grappling with scale dependence for a long time, and this hierarchy, I hope, gives you a sense of all the different ways in which they can define it. So level 1, here are just a few examples of people who have done these cross-test comparisons, right? What if the domain or dimension itself are different? There's just a brief listing of folks who have grappled with this. Tom Proctor is actually a doctoral student at Iowa who actually created 3 different science tests, right, according to different frameworks, and sent them out into the field. And this is one of the things you can do in Iowa when you have the whole state as your lab. But he sent 3 different science tests out into the field and tried to see how growth trajectories, how measures of growth and scaling changed across the different tests, right? And so others, John Pape, who's a student at Harvard, also did these sort of cross-test comparisons and compared value-added metrics across different tests, right? And this is scale dependence, but it's really like swapping out one scale and putting in a completely different one that should ostensibly be similar. So comparing results across different tests or dimensions is one thing that one can do. In level 2, we can talk about equating designs and scaling decisions. This is more psychometric, and I just wanted to present this because this is a problem that psychometricians deal with often. We often have 2 different tests given at different times to different people, right? And so the tests are constructed differently, right? We can't use the exact same test questions year to year. So what we actually have to do is say, at what point on this scale, corresponds to an equal level of proficiency on this scale? And there are actually a bunch of different ways that this is done, and a number of different models that we can use. And so a lot of psychometricians can take a look at this and say, okay, let's look at all the plausible ways that we can create these links and see if that makes differences for our ultimate metrics. And here's just a couple of examples of folks who have done that, comparing results across different designs and models. But again, after you've done level 1 and selected a test, and then you've done level 2 and selected a particular equating metric and scaling model, then still at level 3 you have this concern, and this is where I'm going to focus now. So here, this is scale is again an equal interval assumption. This will link back to what Mitchell was saying earlier. Again, an interval of any arbitrary size affords equal interpretations anywhere on the score scale. Interpretations in use, right? It's all downstream. It's like, what are you using this for? So that does, as you mentioned, force us to look at the Rube-Goldberg machine. And so again, this is the idea. Without this assumption, what you can imagine doing is taking your fingers like this and saying, well, if you're telling me that this assumption doesn't hold, then it means I can do this, like squish, like this, and there's no consequence. Or I can stretch this, and there's no consequence. So again, to use some metaphors here, and I should say that this has been done before too, right? So Seltzer, Frank, and Brake compared growth interpretations between two different scales, grade equivalents, which are one transformation, and scale scores that are another. Briggs and Wiedebenner in 2009 compared the effect of these transformations on student growth percentiles, and this is kind of what I showed you earlier. And more recently, Bond and Lang demonstrated how scale transformations can reverse achievement gap trends. And I should mention that Sean has done a bunch of work on this as well, and it's actually what led to some of our recent collaborations. So I take a little bit of a different perspective on level 3 than these particular authors, and I'd like to sort of present that here.
So Andrew,
Yeah.
one question. So you said twice that the equal interval assumption is really about how you use it. It's really downstream. But I think there's a different argument that it's really upstream. That is, there's a real thing you want to measure, and you want your scale to an interval of your scale to represent an interval of the thing you want to measure.
Mm-hmm.
Because the downstream thing worries me because I could say, well, I want to know how test scores relate to wages later on, and so I want my scale to be equal interval in a way that relates to equal amounts of wage differences. But that then becomes dependent on whatever it is that turns test scores into wages down the line, which is whatever the economy looks like or whatnot. And so then what my scale reflects is not the thing I want to measure, like cognitive skill of some sort, but it represents the relationship between the thing I want to measure and the downstream thing. So right. I think you want the interval scale to reflect the thing itself, the thing you want to measure, not the way you want to use it later on.
But then I would say at least then the use has to be informed by what it actually is that you have measured. And so I guess the reason this is interesting because this is where I circled. I'm so used to having the baby chicks taken away from me, that I end up having to do this sort of backward validation, right? And based on however the chick gets taken away and put through this Rube Goldberg machine, I have to come back and sort of backtrack and figure out whether that's justifiable. But I certainly concede that that's a better way to frame it. Let's decide what an interval scale should be on some foundational level, and then that should constrain all future uses of it, right? My concern is, of course, that the uses are very likely to spin out of control, and so that's why I think it's also useful, I guess I would say, to pay attention to how they're used downstream. But I certainly can. I mean, for example, let's take a look at Iowa's developmental score scale. So Iowa has a very thoughtfully constructed vertical scale that shows that you make large amounts of growth gains in early grades and then plateau over time. And they've based this on a lot of the psychological literature in these particular domains, right? And it's not so actually surprising to us, right, that maybe more learning happens in the early grades and maybe less so in 7th and 8th grade, depending on what it is that you have. So if you use that thoughtlessly, if you just looked at gain scores in 3rd grade and 4th grade, you'd be concluding potentially that like teachers and schools are making, are responsible for lots of growth in the early grades, and all of a sudden 7th and 8th grade teachers are not very good at teaching sort of foundational mathematical concepts, for example. Right, and so that's why I think as precise as Iowa has been with their scale, they've been forced to come up with new metrics because the uses have not aligned with what the equal intervals are that they've so carefully set up. So I think you're right that upstream matters too, and my focus on downstream is reflexively defensive to all that's been done with test scores over time. Does that help?
Yeah.
Okay. Yeah. So first, I mean, I guess the question is, are transformations ever allowable? And there are folks who are much more, who argue much more for equal interval principles than I do. There are people who believe that they're equal intervals, right? So I want to show you just a little bit about how transformations actually work. This is a raw score scale. So this is the sum of items that you get correct on a particular test. This actually comes from an actual state. And I want to show you just a little bit about how score transformations work in practice, and I think many of you who have taken IRT with Ed or have done some work in it can think of actually IRT as something very simple. It's a no-frills way to describe the practical effects of IRT on distributions is compression of central scores and stretching of extremes. Right, so the practical effect of IRT, there's all the dancing around that we do with the logistic model and what have you. The practical effect is usually what happens is this. Right, so usually what happens is something like this. And don't pay attention to the shift of the distribution as much as the fact that look at all these scores here. They kind of get compressed over here, and then we kind of have this, look at that. Right, we kind of have this stretching that goes on over here. Right, and so this is as a matter of practical impact what a lot of IRT transformations do, and there are those this is a very practical model that leads to a lot of useful useful activities. But there are those who think that those activities are so useful that we should really rely on this ultimate scale as the equal interval scale. And I'm just going to show you a few arguments that push back against that. So does the resulting scale have strong equal interval argument? So Lord, way back when he was really pioneering in this field, demonstrated that any particular IRT theta scale, while mathematically convenient, holds no obvious theoretical advantage over any other transformation thereof. Which is one way to put it that I think is quite convincing is to say that the data themselves cannot distinguish between any theta and any particular nonlinear transformation of theta. Right, so the data can't tell you, right, that there's anything that's more useful about one transformation than another. After the model has been fit. And so Yen and Zwick, similarly, the test score scales hold no strong equal interval argument with respect to the psychological construct or educational domain being measured. So IRT, which is often used as saying like, well, it creates these kind of equal intervals, I don't think is a be-all, end-all argument for saying that this holds. So does this mean that any transformation is permissible? Can we arbitrarily make distributions, say, U-shaped? Right, and I can do that. Did you see that distribution that I showed earlier? I can push the middle scores out, right, compress them like at the extreme ranges, and I can make a U-shaped distribution. So if I really don't believe in this, I can do anything I want, right? And so, like, what I'm trying to do in this presentation is again to try to establish some middle ground between the ordinal and the interval, which says, you know what, you can't make a U-shaped distribution. I mean, that's just ridiculous. So there are some transformations that aren't permissible. And there's a log normal distribution, and I'll show you what that looks like in a second. Is that permissible? So once we dig deep into the weeds here, we can see that the idea is that the scales are pliable, but arguably not like breakable. I would call like creating a U-shaped distribution, kind of breaking the scale. And I think we should think of the practice of shifting our vision as a pliability argument, right? So this is pliable between the ordinal and the interval. And so the idea here is like, imagine that adjacent numbers seem to sway as if adjoined by springs. Right? And so here's you like my clip art here? But the idea here is that, so that's the idea is that, we can compress this a little, but not too much. We can stretch this a little, but not to the point of breaking. Right? And so that's the idea that, that's the sort of perspective that I like to take. And again, I think in our field we're either forced to say, by matters of convenience, we're either forced to say, let's believe the equal interval scale, or let's go all the way over and say we have to pick methods that are invariant to any transformations. And I think there's a middle ground. So successive distances are not only uneven, but seem to expand and contract unpredictably. And this is what I mean by the glasses. Right, that we shift our vision a little bit and start to see the swaying. And that's also the metaphor of the building, right? So that the building is swaying a little bit, but not a lot. Right? It's not like we have to create our buildings, our metrics, to withstand like 15.0 earthquakes. Right? There's this like level of expectation up to which, right, we can say we need to protect our metrics, but not beyond. Okay. So the springs are not infinitely compressible and stretchable. The scale is pliable, neither ordinal nor interval. Its equal interval argument is weak, but not baseless. So then the question becomes, how do we determine what a plausible transformation is. Where do we set the mark on like how much our springs can be compressed or stretched? So imagine if we could say like a distribution can look like this, which is a normal distribution, which looks completely normal, familiar, but it cannot look like this, and this is a log normal distribution. Right? And so we can say, you know what, this is just a little bit too extreme. And so that's the discussion I'd like to have. Right? Because once you concede that some transformations are permissible and others might not be, then the game becomes, right, how to figure out a framework through which we can communicate and have a discussion about which transformations are permissible and which ones are not. That's my goal right now, is to provide not the answer to what a plausible transformation is and is not, but provide a framework that allows us to communicate and agree upon what a plausible transformation is. There's a reason I think this is an important thing to do. And that's because addressing scale dependence is important, but it's really hard to do at levels 1 and 2, although Sean is doing this and others are as well. So describing scale dependence is difficult practically at levels 1 and 2. At level 1, we require alternative domain definitions or alternative tests that represent them. And thankfully, NAEP has done an incredible job of being just that audit. Right? And we do a lot of state NAEP comparisons, but NAEP isn't everywhere at all times, and I think we need to address scale dependence in a different way, beyond just NAEP comparisons. So it's not always possible to do this, right? To switch out the scale fundamentally to address this. At level 2, we require alternative equating designs or raw item level data to implement different scaling models, and this is also impractical. Right? It's hard to go back to the to the item level responses. We usually get scores, if that, right? So it's really hard to run through a bunch of different models and express this. But I actually think it's very easy to address level 3 scale dependence. Relatively easy to address level 3 scale dependence, and I hope to offer you an approach of how to do this. Okay. So here's the practicality at level 3. At level 3, there's a potential for a simple, general, standardized scale sensitivity procedure for any accountability metric. So I'd like you to imagine that you have, in your Stata file or your R file or your MATLAB or Excel file, you've got a column of data that represent your test scores. And then what I want you to do is start putting on your glasses and doing this a little bit. And so you'll get a bunch of other columns of data that represent your plausible transformations. Then repeat your approach and see if it makes a difference. Okay, so that's the simple pitch, right? So take existing scores, apply a family of plausible transformations. Now you have all these other columns of data, right? Calculate your accountability metrics, shove them through whatever process you like, right? Send them off into the wild and be done with them, whatever is done with them. And from each plausibly transformed data set, we can assess the robustness of interpretations of metrics across these plausible transformations. Did it make a difference? Did distorting our glasses, our lenses, have an impact? So this begs the question of plausibility. How do we determine which transformations are plausible? That's what I'll turn to now. This is one of many approaches, but what I'd like to do is show you a kind of hopefully useful framework that allows you to talk about what's plausible and what's not. And so first I'm going to reference plausibility to skewness. And skewness, just to remind you, this is where I do my distribution dance. But actually, the story is that even I get confused still with what's positive skew and what's negative skew.
I'm
so
glad to hear you say that.
Right. So I think the idea is that so the skew is the direction that the tail is pulled. Right. And I think that what I always got confused with is that it looks like this is like a slug that's moving in that direction. Right? It looks like the head of the distribution is kind of tilting that way. So you think it's positive skew, and in fact this is negative skew. Right? So that's always confusing, but I think it's important to talk about this because this is the idea. Again, we're going to say that whatever distribution we have could actually look like this. Right? Which is exactly what I did here, right? When I talked about pinching and stretching the distributions. Right, so that's the idea, is that we can reference plausibility to skewness, where that is negative skew, and this is positive skew. This is the direction that the tail is pulled. Okay. So this, for example, is a skew normal family with skewness ranging from -1 to 1, but I want to go beyond this family. Okay. I also want to reference plausibility to kurtosis, and kurtosis is the fourth moment. This is a little bit harder to do, but I want to do a little bit of a distribution dance here too. So this is from Wikipedia. Thank you, Wikipedia. But the idea is that the kurtosis is peakedness and also heavy tails. So when you talk about high kurtosis, you kind of want to stand up and then flap your arms. Right, so that's the idea, is that there are heavy tails, and also you're pretty peaked. So you can see peaked. So this is like high kurtosis here, and you can kind of see out there at the end that that has the heaviest tails, right? So that's high kurtosis, and then this is low kurtosis, right, where you're squat and have weak tails. And that, as you can see, are these distributions here that are kind of squatter and have weaker tails. Okay. So the idea is any test score distribution that you have, you start to do this little dance. All right, you start to say, okay, you've got a test score distribution, and it could look like this, or it could look like this, or it could look like this, or it could look like that. Right? And that's the idea, that's the glasses. And so then the question is, did that make a difference? Right? Did that have any impact? Because maybe those transformations are permissible, but breaking my arm off and sending it out over there is not permissible. Right? So that's the pitch. So leptokurtic, high kurtosis is peaked and heavy tails. They call it platykurtic, or low kurtosis is flat, weak tails. Okay. So I've actually, also kurtosis, just so you know, ranges from 0 to infinity, and normal is 3. So like if you have a distribution with a kurtosis of 2 or 1, we call that platykurtic. If you have a kurtosis of 20 or 100, that's leptokurtic. So you like how far back this is going in time. I actually, relatively recently, I had a bunch of different ways of thinking about plausible transformations. Bond and Lang has one, and Sean has one, and so I find this to be, and I'd like to hear your thoughts on it. I find this to be a useful way to talk about plausible transformations, because you can actually visualize them in a useful way. And this goes back to Pearson, one of the Pearson's, Pearson's distribution system. And so you can actually create a plot of kurtosis, and by convention we go down with the scale, which is a little bit strange, and over, and that squared skewness across the top. Okay, and what he actually shows is that in this space you have distributions that may sound familiar to you, to some of you, particularly those of you who have dealt with statistics and particularly Bayesian statistics. So first of all, there is an impossible area. You cannot create any kind of distribution that sits in this area. You cannot have a highly skewed distribution with low kurtosis. Right? You can actually think about that, right? If you had a highly skewed distribution, it means you have like some tails. Right? So you can't have a very highly skewed distribution with like that low kurtosis. So there's actually an impossible area here. Your normal distribution, your normal distribution sits there. Right? So this is kind of, you can think of this as kind of a baseline, like what we are commonly might expect to see in real score distributions might be something that's kind of based there. Again, a kurtosis of 3, and you know that normal distributions are not skewed. Right? What's interesting again is that in this space we can start to see other distributions that are familiar. This was what Pearson called the type 1 distribution, which is actually a beta distribution, which I'll show you in a moment. So beta distributions all sit in this space. Right? They're constrained by their parameterization to sit only in this space. Over here is a symmetric beta distribution, which I can show you later. This line right here is what Pearson called a type 3 or gamma distribution, and some of you may be familiar with gamma distributions. This is what we called a type 4, which we now call an asymmetric T distribution. By the way, back in the day, they didn't have the term beta distribution. This is called like a Pearson type 1 distribution. It's kind of interesting. So this is going historical here, as you can see. This is a type 5, an inverse gamma distribution, and here, stuck in the middle here, is an F distribution. These are your F tests, right, that you do in regression so often. Okay. So these distributions, which you may know, the chi-square is in here too. And by the way, over here is your T distribution, like a T statistic. Right? And so T distributions, they start to look normal once they reach a certain point, right? But otherwise, for low degrees of freedom, start to go way down there. Right? Become very peaked. Right, so this I thought was kind of neat, and for those of you who deal with statistics and different distributions, it's kind of neat to see everything kind of fitting together in this little puzzle. And I found this very appealing. I think I'm a very visual person, so I really like this. And again, it allows us to kind of see what distributions could be like, and from there create bounds to talk about what a plausible transformation might be. Okay, so it's kind of, I acknowledge it's ad hoc, but it's maybe a useful framework for talking about this. What I actually here. So I'll do that in a second. This is what I might call a descriptive approach to plausible transformations. And the idea is, what if I referenced plausible transformations to the distributions that I see in practice. So take observed state test score distribution, state level representing 17 states, reading and mathematics, grades 3 to grade. And I want to see what they look like on this map. Right? And so I'm going to include raw scores in red for states that publish them, display scale scores in blue, and I'm going to plot the squared skewness and kurtosis of the distributions in the Pearson diagram. So I'm going to say, let's talk about plausibility, but let's reference it to what I see in practice. Right? And that's not the only way one could do it, but it's a way of getting a baseline. Right? What's crazy? This defines plausibility in terms of state-level test score distributions seen in practice. And that may not be the be-all, end-all, but it's one empirical baseline. Right? What do we see? And so this, again, is our Pearson diagram. And this is what we see in practice. So these dots all correspond to state test score distributions in the real world. And the idea is there is one state subject grade combination that has a kurtosis of around 7 and a squared skewness of just over 1. Right, so this tells me that family of distributions I showed you earlier, which you call skew normal distribution, might not be sufficient to capture the kind of skewness we see in practice. Because look, we see skewed distributions that are even outside of 1. Okay, so this is the idea, and I kind of want to show you a little bit about. This is a nod to Ed, too. As far as these are sliders. these are some sliders. I did decide to do this. So this is actually something that was from the SRI workshop that some of you attended. So this is a beta distribution. So I'm going to show you how changing the parameters of the beta distribution creates distributions that dance in this area. Right, I'm going to show you later how F distributions dance in this area. So let's look at the red dot right there, because that corresponds to the beta distribution. What I'm going to do is I'm going to take this parameter and create something of a skewed distribution. Skewed positive or negative? Negative. Right? Right, but so what did you see there is that dot that corresponds to the skewness and kurtosis of this distribution is moving around in this space. Right? And so what we can do is say, okay, look, and here I'm pushing it out a little further, and I can sort of say, okay, at what point does something become crazy? Right? And so what I've actually shown you here is, and I jumped the gun here, but this is like what I might call a plausible area. Right? If we draw in this space, we might be able to say, look, that beta distribution just got a little too crazy. Right? It started to break the springs a little bit. Right? And by the way, this should feel really fuzzy to you. Right? It should be like, how do we make that cutoff? But I'll remind you that we make these cutoffs in real world situations all the time. Alpha equals 0.05 anybody. Right? That's a cutoff. And we say power is equal to 0.8. That's a cutoff. Yeah. Right? So this is not too crazy. The question is, what is a framework that allows us to talk about this, and so that we're all on the same page about the cutoff that we happen to be selecting. Okay. So that's the beta distribution, and now if you follow the blue dot here, I'll show you the F distribution, right? So this is dancing, so this is changing the shape of the F distribution here, and you see that blue dot just moved over here as this distribution changed its shape, right? And so that's, again, creating distributions that are dancing around, and what I'm saying is at a certain point, this F distribution becomes a little too skewed, right, to be what we might think of as plausible. Okay. So I'm hoping that this framework, and I'm not totally wedded to it, but I think we need something like this. This framework will allow us to communicate about what is plausible and what is not. Okay. So this is what I was getting at, right? The idea here is that I might say, this is plausible. And if you disagree with me, that's fine. But at least we can agree about the disagreement. Right? At least we have a framework where you say, I want this to be out here, or I really want this to be here. Right? And it's a framework that allows us to discuss and debate the limits of plausible transformations. And conditional on that, once we agree, then we can talk about the scale dependence of anything. Right? We can sample in the space, transform our metrics in that area, and then talk about scale dependence. Okay. One thing I want you to notice here too is those are the raw score distributions. They actually map very closely, for those who know it, to a beta binomial distribution, which is actually what a very useful model for raw score distributions. And you'll see that what happened was that what IRT does, remember, is compress the center and stretch out the tails. What does that do to kurtosis? So for kurtosis, it actually lowers on the graph, that's right. So on the graph it goes, so kurtosis is about peakedness and heavy tails. And so IRT, right, does exactly that. It stretches out the tail. And so you can see the act of rescaling very visually here, and that it takes all these raw score distributions and brings them down here, right, into a place of high kurtosis. And that's what IRT scaling does. I want to show you a little bit of the border cases, right? So this is what I'm saying. These are the limits of plausibility. Okay, so these are the extremes in this space, right? So I want to show you what they look like. And by the way, I think anyone who's doing this exercise needs to do this, right? How extreme might my distributions look? So these are the border cases. There's a t-distribution with kurtosis of 20. It may not look it because you don't really have a reference, but it has pretty heavy tails and it's kind of peaked. It's kind of hard to see. Here's a beta distribution with kurtosis 2. And actually, I do have a normal distribution as a reference in black, and you can see that the t-distribution is yeah. Okay. I want to also show you, here's another border case. These are the asymmetric t-distributions. So here's a normal distribution. And this is how skewed I'm allowing this to go. And I'm showing you also the log normal distribution that's a dotted line, and just showing you the log normal distribution is too much. All right, so the asymmetric t-distributions go up to a skewness of 2 and a kurtosis of 14 or 20. And the log normal distribution has a skewness of 6, which is off the map that I drew. And again, what the framework allows us to do is say, look, I don't see anything that looks log normal in practice. So that's too much. Okay? And kurtosis of 21, which may be borderline, but the skewness really takes it off the map. Right? And so now, there are alternatives, right? So what Sean has done and Bond and Lang have done, for example, is they've used these polynomial transformations, which are very, very convenient. And I think that's great. What I'd like to do is see that mapped on to this framework, right? As a result of a polynomial transformation, you can transform, for example, a baseline normal distribution, see what the resulting skewness and kurtosis is, and then we can, again, talk about that in this map as well. So this is not bound to using fixed Pearson distributions. Whatever transformation we'd like to show can be sort of mapped into this space that allows us to talk about it and then establish the limits of transformations. But here's what I don't, and Sean definitely doesn't do this, but Bond and Lang have a very useful approach of saying what transformation is possible that can reverse an achievement gap trend. And I think that's a very useful thing to be able to do. But I want to be able to say, you know what? That transformation is completely crazy, or it's completely plausible. And without an appreciation of this distance between ordinal and interval, right, we're not going to be able to talk about that. Right, so I am not so nihilistic that I think any transformation is possible. And this framework gives us a way to establish this. So there are many additional, I'm not saying this solves all the problems, there are many additional things to consider as well, and I'll just mention a few to start. So beyond selecting a boundary for the family of plausible transformations, we also have to address a number of issues. Should the same transformation be applied to all distributions at once? Because we have more than one test score distribution. Should they be applied to all distributions at once, or should different transformations be applied to different distributions? Right, and so that's something one would have to decide and be clear about. If many distributions are on the same scale, should the transformation be applied to a single reference distribution or the mixture distribution of all of them? Right, so again, on the Iowa scale, if you look at their distributions, they've got 3rd grade, 4th grade, 5th grade, 6th grade, 7th grade, 8th grade. So where do you set the transformation? Right, and you have to transform all, if you want to transform all of them at once, you have to figure out some reference distribution to transform. Should transformations be applied to standardized distributions or normalized distributions? I was talking with Jim about this morning. My instinct is to apply it to standardized distributions, not normalized distributions. What does that mean? The idea is, what's the baseline from which we establish pliability? Right, so do I take the existing score scale and then stretch and squish? So what's my baseline for my glasses? So is it the distribution that I first see, or do I want to set some really arbitrary sort of baseline. And so, by the way, I was talking about this in an email with Ed too, that in economics, they often say normalized. When psychometrics, we call that standardized, right? So that's just I was joking in the email about economist to psychometrician dictionary, right? Like, so we could like understand each other, because really we're saying the same things, we just are using different words. So in any case, standardized takes the distribution, no matter what its shape, and puts it on 0 and standard deviation 1. Normalized takes the distribution and distorts it, transforms it to be as close to normal as possible. So that's why in psychometrics we reserve the term normalized to where you actually try to force a distribution to be as close to normal as possible. And then should a range statistic be used to describe the differences, and we talked about this morning too, should a range statistic be used to describe differences or some kind of standard deviation? Right, so do we say like, okay, as I distort my glasses, I'm going to see a bunch of different pictures. Do I want to take the most extreme ones and take the difference? Or do I want to kind of take an average, right? So we talk about standard deviation across what I see. Right, so all of these decisions we have to come to some agreement on them. But this is at least a roadmap, so we can be clear about what we're talking about. So this is actually a picture about standardization and normalization. So this is a standardized version of the distribution that I showed you earlier. All I did was, it didn't change shape at all. All I did was move it over to 0 and make the standard deviation 1. This is normalization. Standardization, normalization. Right, so you can actually see here that we've squished the middle even more. And so the question is, where do you want to start as your baseline for changing your goggles? So I'm going to adhere to the normalization approach for now, even if by default I think a standardization approach is better. So I'm going to talk now. Okay, I have time. So I'm going to talk now about, I'll leave some time for questions. I want to talk now about the pliability of achievement gaps, and this is a term I'll use. Pliability is sort of synonymous here with scale dependence, right, at level 3. Okay, so here's the pliability of achievement gaps. This is something that Sean and I have motivated some of Sean and my work. So here are two distributions that are separated by one standard deviation unit. And the question is, what if we did that, right? And if I don't have a strong equal interval argument, right, then doing this is permissible. And I better be able to say whether my metric, right, could just as well be 1 or something other than 1. Right, so under that family of plausible transformations, this gap actually tends to differ by around 4.04 standard deviations, right, under the family of plausible transformations. Right, so that's a range statistic, right? It goes between plus or minus 0.04 standard deviation units. So that motivates, right, the fact that average difference can be distorted is worth knowing, right? It might flip an interpretation or two. So, what's interesting is that not all achievement gap metrics are distortable. The pliability of gap representations was what led to some of my earlier work on non-parametric or ordinal representation of achievement gaps that I did with Ed. And Sean and I actually, with a number of students in the room, led symposia on these methods at 8-year and NCME this year, extending from a paper that we wrote that got published last year. And also, I should acknowledge Ken, Eric, Rachel, and Demetra here. Who contributed. We came up with, in this line of work, a statistic that is not distortable. So using our approaches that we introduce here, the gap above is 1 in both of those cases, and under any possible transformation. Right. So the idea is, okay, you want to give me your plausible transformations, line them up, give me all the possible transformations you want, and I'm going to give you the same answer. It's going to be 1. Right. So that's kind of useful, right? So that's the idea here, is that some metrics are more pliable than others. Some buildings will crumble and others might not. So the pliability perspective motivates this prior work. 4% may not be much for one gap. You might say, all right, plus or minus 0.04, whatever. But it may be significant for gap trends or cross-test gap comparisons. Right? So then it depends again on what your ultimate research question is. So this is something to note too. There's an impliability to the idea of proficiency. So proficiency is one of the metrics I like to hate. I love to hate. But it's one. I should give them credit for one thing, and that is that they're pretty impliable to to transformations. If I set a cut score here, and then I distort it, right? As long as the cut score is transformed along with the scale, the percentages above the cut score remain the same. Right, so as long as I take this and move that there along with everything else in this distribution, I can take these students here and move them out to infinity for all I care. They're still above the cut score. Right, so percents of proficient students arguably are not dependent on level 3 scaling decisions. Right, turns out that proficiency for all its problems, and Holland has made a point about this too, is at least invariant to level 3 scale transformations. And so again, some metrics are scale invariant. Or more scale invariant or less scale invariant. Here's one that's scale invariant. So now I'm going to mention applicability. This is what led to the finding I presented earlier. What's applicability of student growth percentiles, which are, again, are a widely used metric, right? So student growth percentiles, they are sit on a 1 to 99 scale, indicate student performance above and beyond expectations given past scores. So they use a spline-based quantile regression procedure. It makes them fairly robust to transformations. And so this is actually what motivates the student growth percentiles overall. So the question is, are student growth percentiles really scale invariant? And the answer is pretty much yeah. And so here's an approach that shows this. So this is on the vertical axis here, I have the range of student growth percentiles under transformations. So this person right here has a baseline SGP of around like 18. And then I transformed all of her scores. And I looked across all of those scores and said, what's the minimum SGP she got? And what's the maximum SGP she got? And that range was actually 50. Right, so that's pretty big. Right? That student actually shifted a lot under this family of plausible transformations. But on average, if you look at all the students, and there are a lot of them here, right? On average, the range of individual SGPs is 4 under scale transformations. The median range across all of these is 3. And this is what led to the table I showed earlier. So this actually looks pretty bad, but on average, it's not that scale invariant. It's not that scale dependent. Okay, so this is 27,000, so yeah, we're going to get a lot of bumps here with 3 prior years.
So, Andrew, can you just explain briefly what student growth percentiles are?
Oh, that's another talk. So student growth percentiles. So the way that Damien likes to explain them, which is mostly correct, and will suffice for this presentation, is that you take all of your academic peers. So take all of your past scores and try to find all the people that have similar scores, and then ask where you sit in that distribution. So if, let's say, I go out and find 100 of the, or 99, whatever, 100 of people who have similar past score histories to me, and I get them all in a row, and I say, now let's look at our current score. And I scored at the top. Right? I'm the best out of everyone who has the same score history, so I get a 99. Right? And so it's a little bit more, obviously under the hood we're doing some regression. And I can refer you to some of the work that Catherine Castellano and I have done, and she might. She's a colleague of mine who's done a lot of work. I consider her and Damien the SGP, and a few other people the SGP experts. But that's basically how it works. So this is a kind of performance above and beyond expectation, right? Given all of that, the 100 people in that room, I kind of expect myself to be kind of in the middle, but I really exceeded those expectations, so I get a 99. Why don't I jump ahead here? So this actually leads to more of a value-added type approach. Yep.
Oh, I just had a question about the previous graph.
Yep.
Is there anything that's sort of predictive of those ranges that you estimated?
Yes. Yes. They're easier to show here. Let me just say that maybe I should have talked about. Yes is the short answer. Here's where I wish I had a big thing to draw on. But given here's a different approach. Let me just jump into this and talk about how you can expect to see this, right? So here, this is a similar metric that Catherine and I have developed that says do a linear regression and get your expected score given your past scores. So I think everyone in this room knows how to do that, right? So I have 4 variables, and instead I type regress the most recent score on the 3 previous scores. And then I get an expected score for me, given my 3 past scores. Then I can ask, did I do better than that expectation? And that's a residual, right? So that's a performance beyond expectation. Then I can just take the percentile rank of those residuals, and those correlate about 0.99 with student growth percentiles. So the idea is that we can sort of demystify student growth percentiles a little bit and just talk about them as the percentile ranks of residuals and get away with a lot, right? So in this case, this is what we see, however, right? Under these transformations, right, percentile ranks, this linear, because we have a linear model here, we actually, on average, the range of individual PRRs is 12 under scale transformations. It was 3 for student growth percentiles. Right, so that is to say that the PRR metric, which is very, very simple, is unsurprisingly, I think, to those of you who know linear regression, right? We start to skew things. Linear regression tends to, just like correlations, tend to follow these outliers. And so you're going to get just greater distortion. Right? And so we actually advocate for PRRs. They're very, very simple. But it is true that student growth percentiles are more scale invariant. Right? That is a useful feature. Now, they're not totally scale invariant as we've shown, but they are more scale invariant. Now, to get to your question, right? I mean, we see these interesting sort of patterns here. What's going on, right? Do you see this like under the hood here is like this funny like. Right? So I can sort of draw that. This has to do with leverage for those of you who have dealt with. Anyway, so at the kind of extremes, they also tend to have kind of a lot of pull. And so I think that that's what helps to explain part of this. So the short answer is yes, if you look under the hood, there are ways to appreciate how a metric is more or less scale invariant and exactly where that is likely to be. So that's a good point. So what I did want to get to this, and this is like a mean student growth percentile, and this is actually very close to what is used as a kind of functioning, effective, value-added metric in a lot of states. What they do is they take all of your student growth percentiles and they take the median. And actually in some of the work that Catherine and I did, we encourage them to take the mean because it ends up like cutting your variance. Means are more precise than medians. We quantify exactly how much. And although medians are widely used, we show that means are far preferable. And note that the range of mean SGPs is more narrow. So this is actually from the same data set for cohorts. And so these are mean student growth percentiles. And again, so this is a teacher who on average taught students who had high SGPs, right? And so they performed better than expected. Right? And so this is again functioning as a kind of quasi-value-added metric, and the extent to which this changes, right, over plausible transformations may be consequential. Right. So, but overall, on average, the range of mean SGPs is 0.8 under scale transformations. The median range is 0.7. The whole pitch here is you can do this with anything. Any metric that you might have, you can put on the glasses, torque things a little bit, and see how much the range or standard deviation might be. So I'll jump through. So again, these are kind of the form of the findings. Right, and my point here is that we can do this for a whole range of metrics. We can compare a bunch of gap statistics. I already mentioned 2, right? Differences in averages, and the metrics, the non-parametric metrics that Sean and I and this group has been working on. And so, one is completely scale invariant, and the other depends. And we can talk about how much it depends. And that I think is a very useful thing to be able to do. Right. So. So it's kind of like, but I want to be kind of careful about this. It's kind of like a scale-induced kind of error, right? And it's not, error is a dangerous term to use, but you can sort of think of it as loosely analogous, and here I hesitate. So this is kind of an effort to communicate the sensitivity or pliability of accountability metrics to plausible scale transformations. It results on a kind of error bar, right, around any given statistic that you might have. That addresses the vagaries of scale. And note, I should note here that the traditional error and scale transformations actually interact. Right? As I change my scale, the error structure changes as well. So that's important. That's why I'm sort of being cautious here. That said, again, anything that you see, you should be able to change your vision. And that's kind of like, it's kind of analogous to a confidence interval, right, for sampling. So it's kind of like a scaling version of that. So clearly this depends on how we delineate the family of plausible transformations, right? So that clearly it depends on this trapezoid, right, and how we'd like to shape it. And this is arbitrary, but though arguably not that much more arbitrary than setting a 95% versus 90% confidence interval. Right, so that's the analogy I'm hoping to create here. And so this is like a way of describing dependence that I think is underappreciated in our current practice. So why does this matter now in particular? So individual scores at a single time point can be transformed, but rankings typically don't change. And Claude and I were actually talking about this in our talk today. He said, what about selection in this issue, right? And I actually said, well, selection I'm actually not that worried about. Right? Well, the people above the cut score are still going to be the people above the cut score after I transform them. Right? So it's more in this era of aggregation and adjustment that this problem has become a serious issue. Right? So as long as why is it that we haven't been talking as much about this, right? And why is it that this matters more now? So arguably, level 3 has been a negligible issue for individual single time point interpretations. Because people are still ranked in the same way, and that might have been the only inferences we really cared about. But with the rise of accountability metrics and increasingly complex calculations and adjustments, from growth to gap trends to value added, for example, I'm trying to argue that scale pliability is no longer negligible. It's definitely something we need to put on our radar. And not only put it on our radar, not only have a method to do it, but to be able to talk about it. And that's really what I hope this framework does. It allows us to at least say, okay, you want to do plausible scale transformation, show me where they are in a map. And then we'll disagree about, or agree about, wherever the bounds are. So what I've tried to do today is give you a useful framework for thinking about scale dependence, and I've tried to establish a space kind of theoretically between the ordinal and the interval, because only then I think we'll be able to productively talk about scale dependence, right? So there are such things as pliable scales, but not breakable scales, right? And plausible transformations. So what I hope is that this leads to a kind of standardized, practical method for reporting the scale dependence of accountability metrics more generally. Right, so again, whenever you see a variable that's in your data set or what have you, that you could push a button and it would generate, according to some parameters, right, 10, 50, 100 more, replicate your analysis, see if your findings change. And I think we need to not just have that ability, but be able to talk about the assumptions that go into creating all those additional variables and talk about whether those are plausible. So I hope the Pearson family has done that, and thank you for your time today. We have about 15 minutes for questions. Ben?
I'd like to go, this is great fun, thank you. And I like the graphics, and just to set the record straight, you taught me how to do slides. I'd like to go back to this question of defining what equal interval means, sort of upstream versus downstream. And I agree with the importance of trying to say, in the first instance, what we have and how our scale relates to something that's underlying. But I don't know how to talk about that without referring it to some interpretation.
Mm-hmm.
With your example of developmental scales with children, we know that they start out rising steeply and then taper off because we're referencing them to growth or time.
Mm-hmm.
And I don't know, we want to keep those interpretations close in, but are there any ways we can talk about what equal interval means without taking one step out at least to some kind of interpretation or statement about the meaning of the score scale?
I can leave and let you and Sean hash that out. But I'm very sympathetic to exactly what you said. I find myself, and this goes back to Michael Kane's work and the validation work that you've been writing about recently too, is that in scores, we don't talk about, in testing, we don't talk about whether a test is valid. We don't talk about whether a score is valid. Actually, I should rephrase that. A lot of us do. A lot of people out there do that. Psychometricians prefer not to talk about whether a test is valid, because a test that one might think would be valid could easily be used for some use or interpretation that is not justifiable, right? So validation in recent years, first of all, we call it validation, not validity, because we think of it as an ongoing process. And second, we think we have to identify first what Michael Kane calls the interpretation and use arguments. Right, so we have to figure out, well, first and foremost, what are the interpretations that are being supported by this score and set of scores, and then what are the uses of these scores. So that's sort of why you can see that I sort of leaned towards the sort of downstream, and so I'm sympathetic.
you've written recently that our question should not be what's your interpretive argument, our question should be why didn't we see this coming?
That's right. I've been talking with Jack Buckley, who's the director of NCES, and he was saying, like, I think it was maybe a year or two ago at AURA, he was saying, Andrew, I don't want to be in the position where I have to defend any possible use of test scores. Right? I mean, like, I don't want to have to be put in a position where it's like I have to see everything coming. To which I would concede, and I actually didn't have a response to that at the time. I was like, that's a really good point, Jack. But like upon reflection, like we should know exactly how. I mean, there are these known vectors, right? I've called this like an epidemiological perspective on test score use, right? There are these known vectors that take test scores and carry them off in known directions, and we have historical demonstrations that these are increasingly likely over time. So we can think of this as like the spread of the disease, as predictable as the spread of the flu from Southeast Asia to like the to the States every winter, right? So we should know it's coming. So I guess to Jack, upon reflection, the idea is like you should be able to defend at least against like the 2 or 3 you can totally see coming, because as psychometricians we've seen it all before.
So I've been reading in the wild and woolly world of science studies lately, and I was sort of wondering if you were too, because of your in the wild metaphor. But one of the things I've been thinking about in that regard is that measurement regimes essentially hold together an extraordinarily diverse division of labor that includes people like you and me and our students, but also educators, regulators, policymakers, consultants, the National Center for Education Statistics. And so, in a sense, there's it may be problematic analytically to talk about what we're trying to do with the measures as psychometricians and what the world does with our measures once we let them out. Because in fact, what the measures do is connect Stanford University's Graduate School of Education with this larger machinery. So it's not like there's Rube Goldberg out there waiting to eat our chick, right? I mean, we're part of the machine ourselves.
You're not letting me off the hook. No.
Yeah. So I mean, so what do we? I mean, why? What? How would your talk be different if you said you're part of the machine and as a member of the machine?
That's a great point. I concede that. Yeah. And so that's exactly why I was saying that we have to. And this is actually Ed just wrote about it. He gave a great talk accepting an award recently, and he was making exactly that point that testing experts have to take more responsibility. If you actually look at the 99 standards, is that right? The 99 standards say that ultimately the responsibility for test use lies with the user, and that's paraphrasing, but I think it's very close to what it actually says. And so that's a great way for the testing community. That's APA, AERA, and NCME saying it's up to you guys. And so I'm actually saying exactly, I'm agreeing with you that it is our responsibility and your responsibility. And you're looking at future testing experts. This is exactly where we need to be playing, and so that I take on full responsibility for that. That's why I'm in this area.
Andrew? Yeah. So I've been sitting here thinking about Liz Cassio and Doug Steger's paper, and wondering if it's just one special case of this,
where
where the parameter of interest is sort of the persistence of learning or knowledge over time, and they sort of pick one common scale transformation that is used a lot in economics, but sort of I wonder if you have thoughts about how to relate that debate about the persistence of learning over time to.
That's exactly. I mean, so this is I think a framework that allows them to locate their scale transformation in this family. And then we can talk about, is that out of bounds? Should we look at more transformations? I think again, so this is the utility of this. I think is great, right? I mean, you can do this anytime you've got a vector of test scores, and so it's exactly I think what they it could hopefully help what Liz and Doug have been doing. I do think there are a lot of issues that I just swept under the rug that are back here that need to be addressed, and it's something that I'm trying to address. Sorry. Right. So there's like this list of additional issues is no small we've got to sort of address these issues, especially when it comes to like multiple score distributions over time, right? And so that's what they're dealing with.
Right.
And so that sort of changes how we might think about the bounds of plausible transformations. But in short, I hope they find this useful. So you can think, do any of you do box-Cox transformations here? Right? I mean, so like in regression, like what we do, well, one response I had to my own, to this line of work, is if you see a skewed distribution, what do you guys do? You transform it, right? So the idea here is that like is this all a problem? Because if I looked at a test score distribution like that, why not just transform it and then be done with it? And the idea is that the point is that if that's what you do, you've got to do that to everything, this way and this way. So what that starts to do is basically apply like the best linearizing transformation to anything before you run it. Right? So it's not to say you should. That's here's what I find interesting about student growth percentiles. What I would do if you don't believe in scale, normalize it. Right? I mean, so what's interesting is that for example, so Damien's work is like he has all these complex like quantile regression splines chasing the data around because the data could be in all these different places. What I find interesting about that is we have a lot of scale nihilists here who are afraid to take the step of just normalizing it, right? Which is to say, don't just standardize. If you don't believe in scale, don't believe in scale. And so that's actually a general metric approach that is scale invariant, because you're basically saying, whenever I see any scale, I'm going to normalize it, and then I'm going to start my work. Right? And so that's actually what I showed in that table. Is I think economists might. And I'd actually be kind of in favor of this first, transparency. Economists might say, instead of normalizing, normalize, like for real, normalize, right? Give that a shot. If you really have concerns about scale, that should be in your toolbox.
Following up on that, a question I had is, like early on when I was learning regression, someone told me like you should never transform to achieve normality.
Yeah.
Unless you really because you're now measuring something different. Like your variable now means something different.
That's right, exactly right. Yeah.
So I'm kind of wondering how that relates to all this. Like when you go through these transformations, does it really make sense to call what you now have the same thing? Is it measuring that? Like, does that matter?
Yeah. So
this gets a little bit to the upstream, downstream.
This does. Yeah. It really does, and this is actually exactly. When you transform, your coefficient starts to mean something different, right? You're interpreting something on a multiplicative scale, right? So this is all bound up in that. The idea is that, if there were just one skewed distribution, you'd have a solution to it, but you'd have to interpret the coefficient accordingly. But like this is saying, this is the regression assumption we always sweep under the rug in intermediate presentations of regression is the fact that is the equal interval assumption is both measurement error actually and equal interval assumptions. So I think the no transform argument comes from a place that believes in equal intervals. So this kind of throws all of that out of whack. So that's why I think it's important to discuss. Because I guess my answer to that advice is that you're assuming equal interval scales. And if we talk about pliability, we need to get a new host of approaches in our bag.
Finally, thank you. This was our final seminar for the year. It was great. Thanks for coming out, and let's thank you.